As mentioned several times, the core problem in computational imaging is estimation of high-dimensional objects from lower-dimensional measurements. This applies to hyperspectral imaging, video, three-dimensional imaging, and so on. Back in episode 23, we talked about how to use coding to create three-dimensional reconstructions from lower-dimensional measurements with projection tomography. In episode 26, we talked about how this applied broadly to a wide variety of snapshot compressive imaging problems. Today we're going to talk about compressive diffraction tomography, how to represent multidimensional objects from lower dimensional measurements with wave optics. This is an example from Professor Liang Cai's group at Tsinghua University, where the holograms shown at the left are captured in a single frame, and then from these holograms the multidimensional scatter distributions shown at the right are reconstructed. The red curves are the ground truth of a bunch of particles distributed over space. The blue plus signs are the reconstructions using a neural processor, and then at the right we compare the ground truth with the reconstructions. The process of creating these multidimensional projections from single holograms is the topic of today's discussion. Computational imaging. Episode 31, Compressive Diffraction Tomography. Episode 30 discussed diffraction tomography, where we illuminate an object with a wave, measure the scattered wave, and try to estimate the three-dimensional object. As discussed there, if we illuminate with a plane wave with wave vector u0, the scattered field in all directions fills or lies on a shell in the Fourier space of the object, and the diameter of the shell is 2 over lambda. If we rotate the illumination direction, say to this wave vector u1, then the shell that we measure in the Fourier space changes, and by rotating to all directions, we can ultimately sample a sphere in this Fourier space of the object of radius 2 over lambda. If we look from just a single direction, so we're measuring some extent x along a single observation axis, what we're seeing is a slice of the shell of the Fourier space of the object. If we rotate if we rotate the illumination angle, that slice would also rotate in the Fourier space, and so we can sample a sort of bow tie in the Fourier space of the object. Alternatively, we could change the illumination wavelength, which would change the radius of the shell. So in this kind of forward scattering geometry, we see these little changes in the slices that we measure by changing the wavelength. So after we've captured whatever region of the Fourier space of the object we get by observing these various illumination angle, illumination wavelengths, then as discussed last time, we can try to invert that data by any of the inversion algorithms that we've discussed to estimate the multidimensional object. If we think about trying to take the data, which is an incomplete estimate of, or incomplete sample of the Fourier space of the object, and estimate the multidimensional object, that's an example of decompressive inference, and so the measurement could be thought of as compressive measurement and then decompressive estimation. In the case of holography, the idea of estimating a three-dimensional object from a single two-dimensional hologram can be called compressive holography. Here's an example from a paper from 15 years ago where we have a single measured hologram of some dandelion seeds. These are photographs of the individual dandelion seeds. Now, the seeds themselves are at 1.6 centimeters away from the measurement plane and 5.6 centimeters away from the measurement plane. And then they create this measured Gabor hologram. As we've discussed, if we know the hologram, if we use a hologram to measure the field in a plane, then we can backpropagate that field and estimate the field everywhere. If we take that approach here, where we take the measured hologram and backpropagate it, then we reconstruct the field at the various planes away from the object, illustrated here. So this would be the field at the 0 plane, the field at the 80 millimeters or 8 millimeters away, 16 millimeters away, 24 millimeters away, up to 7 centimeters or 70 millimeters away from the object. But what you see is that the field is a three-dimensional object. So we're not estimating the object itself, the scattering object, we're estimating the field, and the field fills the three-dimensional volume. But what we're interested usually in an imaging system would be to estimate the object itself, not the field that created it. So this middle set of plots is using decompressive inference to estimate the object. Now in this case, due to the nature of the algorithm, the object estimated in the zero plane turns out to be related to the zeroth order terms of the, or the DC terms of the Gabor hologram. But we reconstruct the dandelion seeds faithfully at 1.6 centimeters and 5.6 centimeters away from the object. And then in this case, the density of the object is 0 in the planes where there is no object. So we've successfully estimated the object instead of the field. This particular approach, or this particular result, was obtained by taking the measured hologram and using the total variation method discussed back in chapter 3 to estimate the three-dimensional object. When we think about the resolution here, so here we have objects at 1.6 centimeters and 5.6 centimeters. We need to think about, of course, what kind of resolution can we obtain in these systems. As we discussed, the forward scatter for a hologram is a slice of the three-dimensional Fourier transform of the object. The extent of that slice of the Fourier transform along the transverse direction depends on this angle subtended by the measured hologram. The spatial frequency at the edge of the angle is sine theta over lambda. And if we take the full extent of this slice of the Fourier transform, it has an extent of 2 sine theta over lambda. So that would be the maximum spatial frequency in this slice of the Fourier transform. The corresponding transverse resolution would be 1 over that, so lambda over 2 sine theta. Here A is, or A over Z is 2 sine theta, so the transverse resolution that we would get on the object is going to be lambda Z over A. Now, the extent of the region in the Fourier space along the Z direction would be 1 minus cosine theta over lambda, where 1 over lambda would be the full extent of the wave vector, and cosine theta is the part along the Z direction, and this extent is the difference between those two as we go across this angle lambda. If we expand out cosine theta, we'd get 1 minus theta squared, and this theta squared would be, again, this A over Z. So our spatial extent in delta Z actually should be something like 8 lambda Z squared over A squared. So if A was, let's say, 1 centimeter and Z is 10 centimeters, then we would expect somewhere around 1,000 wavelengths, or 1 millimeter sort of longitudinal resolution for this measurement approach. So that kind of tells us the extent of the Fourier space that we sample, and then we use an estimator to reconstruct the object from this subsampled Fourier space. In the example from 15 years ago, that was done with this total variation decompression approach, which achieved kind of reasonable results. But modern systems, of course, use more modern estimators. Recently, of course, people use neural methods to try to estimate the multidimensional object from lower dimensional measurements, and it could be from a single hologram, could be from a set of holograms. Whatever subsampled set of data we have from the diffraction tomography system, we can use that to estimate the multidimensional object. So one approach, of course, would be to model the forward model for a whole bunch of different holographic measurements, and then use training data from a model system or a ground truth set of measurements to try to train a system to do this reconstruction. One of the popular methods, though, has been to use this deep image prior, which does not require training data. In this case, we're doing something very similar to the phase retrieval problem that we talked about a couple episodes ago, where we implement an error regression algorithm. But here, instead of using an inverse propagation as one of the arms on the error regression, we use a neural estimator. So we have the measured hologram, and then we build a neural estimator to estimate the multidimensional object from the measured hologram. But then once we have the estimate of the object, we could estimate what would the hologram have been, and then we can use the difference between the estimated hologram and the measured hologram as a loss function to train the estimator to try to improve the estimate of the multidimensional object. This approach is implemented in a Python notebook that is provided on the GitHub site with this set of lectures. Here's an example of a notebook written by Xiao Wang in my group at the University of Arizona to implement this deep image prior. In this case, we use the minced digits as objects distributed over a simulated three-dimensional volume, and then we try to implement this holographic reconstruction. So here's, of course, we can simulate the measured hologram using angular spectrum propagation. And if we take the hologram and backpropagate it, of course, then we see the background from objects at different planes in each plane, so we don't get a faithful reconstruction of the object. So we can implement a deep prior using the regression loss function so that we have the estimate of the object over the volume, and then we can take the estimated object over the volume and create the hologram and take the difference between the simulated hologram and the measured hologram and train the network to try to minimize that error. We also put a constraint on the hyperparameters or the parameters used in the network, so we want to minimize the complexity of the network that does the estimate, and this kind of minimization structure tends to make the estimated object more faithful. So here's an example of estimation after 1,000 training epochs and showing that we faithfully recover the multidimensional object. Here you can see a simple GIF of this training process. So you start with an initial estimator, and then as the network trains, it turns into a faithful reproduction of the multidimensional object. And here's an example again of the simulated hologram backpropagation, which creates the three-dimensional field with background, and then the estimated three-dimensional object using the deep image prior and the ground truth. These kind of methods have become very, very common, as shown with Professor Sao's work in the introduction. It can be used very practically to estimate distributions over multi-dimensions. This particular technique was pioneered in this work from George Barbastasis' group, the phase imaging with an untrained neural network. This is just one example of many, many examples of ways in which advanced estimators have been used increasingly to estimate multidimensional objects from wave scattering. And this, of course, is a very active and interesting area. And of course, from the perspective of this course, we can analyze the nature of the Fourier space sampling, what kind of data we have. We could analyze coding by using multiple wavelengths and multiple view angles, multiple looks, but at the end of the day, feeding that into an advanced estimator that can estimate the underlying object. So that's our discussion of decompressive or compressive diffraction tomography. Next time, we'll expand this multidimensional analysis to include frequency and time. Here's an example of a movie created by scattering off of a volume hologram of a set of letters that happen to spell out the words Go Illini, back from days when our group was at the University of Illinois. Here, each one of the letters is 200 femtoseconds delayed from the previous letter. So somehow a clever technique is required to capture a video here that plays out over about 15 picoseconds. And so this process of using holographic techniques to capture time will be the focus of our next episode.